here in Rochester, mostly, include Kodak, ITT, Axcelis, Harris, and L3 Harris. Of course, I believe those have all been acquisitions. He has his own consulting company now, KAH Consulting. And over his career, he's held both management and technical roles in support of NASA programs and studies. He just retired recently, but he's still working in support of the Roman Space Telescope, the Chandra X-ray Observatory, and some JWST commissioning activities. He's got a lot of great experience going back to the 80s, and we're excited to have him here. So please welcome up Keith Havey, and I need to cue up.
There are a few people who worked on Chandra, as they call it, or I call it Chandra, but AXAT, Chandra, a few people here who worked on that program for Kodak at the time. Kevin, were you there then?
I was on that program.
The other thing I'll say about my talk, long ago when I was a few years experience, mostly as a thermal engineer at Kodak, and I was working on NASA programs. So I was asked to give a talk about thermal analysis of optical systems at Georgia Tech, and then I had to give one out at University of Arizona. The Georgia Tech one was just students. I went to the University of Arizona, and here's this, cocky 30-year-old trying to tell University of Arizona experts all about all this stuff I thought they didn't know anything about. But as it turned out, I was the rookie in the audience. So I expect here a lot of you are way more knowledgeable when it comes to astronomy, astrophysics, and how the Chandra telescope actually gets used. But I'll talk to you mostly about the engineering side, which is where my experience applies.
Smaller over here.
I want to page down.
You should just be able to click or hit the arrow button.
I click mouse to do it too. Okay. There. Oops.
Yeah, you can use the arrow buttons now.
We got can that screen at the top get moved up?
Yeah.
Is that just drag and drop?
Yeah.
Okay.
Down. Again.
That'll probably work. Yeah. So Chandra is one of the NASA Great Observatory programs, which is a highlight of many years in the 80s and 90s. The development and identification of those programs started actually back in the 70s. HST, we all know, visible near UV, Compton gamma ray, very short wave gamma rays, Chandra, the X-rays, and the Spitzer IR. Chandra was originally known as AXAT, the Advanced X-ray Astrophysics Observatory, specially designed to detect X-ray emissions from very hot regions. And lots of folks have seen the black hole images, typically to make them more interesting, because Chandra doesn't have a lot of collecting area. It detects the high energy particles very, very well, but frequently the best images are when they were overlaid on top of some of these other great observatories, and now most recently on top of the James Webb images, where they're getting much more insight into the black holes. It's pretty cool. L3 Harris, at the time Kodak, supported the support for the program ramped up in the mid-'80s for the Phase B studies. So there was a competition between Lockheed Martin with the Danbury folks, Perkin-Elmer at the time, I believe it was, and then we, Kodak, were teamed up with Northrop Grumman. And basically, we won that competition, which was pretty exciting. I worked on that Phase B study. I was working a number of programs, but I worked part-time in the mid-'80s. So I started working in the '80s. We won the contract in '89. We launched in '99, and it's 2024 now, and I'm still supporting the program. Now, much of that time was part-time. A core element of that period, I was full-time on that program. It was launched on Space Shuttle Columbia. A lot of folks probably know that. Over 400 people at Kodak worked on this project. It filled a really good gap in our in some of our opportunities, and it was a really exciting technology, and I'll go into more detail about some of the work we did. Current status, Chandra X-ray Center is hosted by the Smithsonian Astrophysical Observatory in Cambridge, Mass. The Operations Control Center is in Burlington, Mass. That's where they actually issue commands to the telescope up through the satellite system. In fact, it was interesting when I was working James Webb commissioning, because there were Chandra activities, or if Hubble has a safe mode, but James Webb is trying to commission. So there's all this bartering for time at different ground stations. It's pretty interesting what they have to do. We could probably use a few more ground stations around the world to accommodate as the number of space missions grows. So Chandra is currently funded through 2025 with extension options for 2030. It's a good reason to pay attention to the federal budget. As we say, freeze everything but defense. Guess what? That's NASA. So NASA got a 1% increase this year due to the budget not being passed, and the safe hold level just moves you across at the same budget. So if inflation goes up 8%, you're really taking a decline. So Chandra is still working well. They're hoping for funding through the end of the decade. I did want to say today's presentation is a compilation of previously published papers by myself and others at L3 Harris, as well as NASA folks. And the references are at the end of the presentation. I've got some sheets I printed out with some of the references, or you can just Google. The best website's just chandra.harvard.edu, and it's got excellent information and on the current observations, observation summaries from the last few years. It's got really good background info on the telescope and on the spacecraft and the science instruments. Obviously, it was designed for 5 years on orbit, well beyond 5 years on orbit, but as was Hubble, Gamma Ray, Spitzer. All these telescopes were designed for a few years. In the case of Spitzer, the IR telescope ran out of cryogen after 2 years, but that was by design. And they continued with a warm IR mission with their sensors for many, many years. So these great observatories and today's flagship missions like James Webb, there's a hope they'll all last, much longer than the 5 years. The 5 years is like for the lawyers, so the contract, so people don't have to come back to Kodak and say, wait a minute, your satellite died at 6 years. Like, well, it was designed for 5, so we're good. If anyone online is screenshotting here, just remember, and if there's a copy of this presentation posted, just remember a lot of the images are copyrighted, they're credited to NASA. NASA lets people use them, but they like to see you post credit. And same thing here, these presentations I'm making were from SBIE papers and a compilation of some general notes, some ad-libbing in between those SBIE papers. Just remember to respect the ownership of those, the source. And that's enough of the boring stuff, I hope. Am I going down? Is there a next button? It doesn't seem to work that time. I see it right here. Weird. Okay, so the great observatories, this is probably old news to a lot of you guys, but just a reminder, the US, they were allowed simultaneous viewing of the universe through different windows in the electromagnetic spectrum. So the original names, and I've added the current names for those missions here. And Chandra explores the region between Compton Gamma Ray and the Hubble. And just a little sidebar, these new flagship missions, I just put in the primary wavelengths to study, but it's not just the wavelengths like with James Webb, 0.6 to 28.5. There's a nice bridge between Hubble and Spitzer, but it's also the new technology focal planes and sensors and the collecting area, much being higher. But the wavelengths are important, and obviously that's where we're getting a lot of great discoveries. Roman doesn't go as close on the short wavelength as Hubble, but it's close to the same in the IR, and there's also a great coronagraph being developed for that instrument by JPL for that system. So on this talk, I'm focusing more on the Chandra telescope development. Have broken it up like this. We've done a couple presentations at work for our employees in this format. The early days, the long road to winning the program. We won it, now prove it'll work. There was a very specific congressional challenge I'll talk about in a minute to the X-ray telescope, flight design, and will that work? And then the proof was X-ray testing at Marshall Space Flight Center. And then we were involved in system integration, pre-launch operations, and involved in the flight operations as well. I've just listed a few of the names here. Some of you folks may have run into these folks over the years. John Spina, Senior, listed here. John was the person was a senior systems engineer doing a lot of the technology development and study with Northrop Grumman early in the mission when it was formulating. So he was really key to our technical baseline for the telescope and was deputy program manager after we won that contract. So here's the early days. So back in the 70s, actually back in the 60s, before the HEO payload, I think was from Smithsonian Astrophysics Observatory, was the first demonstration of capability of collecting X-rays. And then in the 70s, the concept with Giovanni and Tenenbaum, I believe are the names, Ricardo Giovanni and Harvey Tenenbaum, were instrumental in putting a proposal in front of NASA for a larger X-ray telescope, building on the early successes that they had. And this is what that early telescope concept that we presented looked like. It doesn't look much like that after it was finally built, but that's what the proposal was. So we were involved in the pre-proposal effort with John Spina. Then we were deeply involved in the actual proposal. And then there was a best and final offer with cost volumes that were, went from the floor to here that you had to study and go through. And the government asked for an audit of our cost estimate. Not only did we have to prove to NASA it was good, we had to go to the Defense Contracting Agency and show them all of our costs back up for this. And it's a little tricky for a company that's worked a lot in the classified arena that you can't tell them where your data came from. The high-resolution mirror assembly uses grazing incidence reflection, resulting in different mirror shapes and long focal length. But obviously, it's kind of a classical telescope, right? You got a parabola and a hyperbola, but these are quite different sections out of those paraboloids and hyperboloids. The nested mirror pairs collect different energy levels, and it's a 10-meter focal length. And for this audience, it'll be pretty obvious. A traditional mirror won't reflect X-rays, but if you go at grazing incidence, much like seeing those irritating headlights reflecting up the black road at night at grazing incidence from that car half a mile away, that grazing incidence, you can get 100% reflectance. So with the iridium coating and the shallow incident angle, they're able to reflect and get that energy from X-ray events at the focal plane 10 meters away. So big technical achievement early in the mission. I mentioned a congressional milestone. They had to prove that they could fabricate these really large mirrors out of Zerodor and then align them and polish them such that they would reflect X-rays effectively. And NASA, the Congress wasn't convinced at the time that this technology wasn't too risky to go ahead with the missions. And so basically the government set up a congressional milestone that said you have to prove to us that you're going to get the image quality you promised here in a demonstration with real flight mirrors before 2 years after the program had started. A pretty aggressive challenge for a program that was so young. So Our part, so PerkinElmer in Danbury was responsible for fabricating the mirrors. NASA had been doing technology development with them. So they fabricated the mirrors. Our job was to develop the metrology systems, the assembly systems, the lifting and alignment systems like you see here to align and put together these four concentric telescopes. Basically, you got to force, as we flew, four. At this time, we actually had 6 separate mirrors. And I'll talk about that in a second. But on the right is one of the coated with the iridium coating on the mirror. On the left is part of the Vita 1, the demonstration for the congressional milestone. And all of this hardware was custom, had to be developed. How do you lift these optics? How do you position them to tenths of a thousandths of an inch? You know, pretty tight numbers. So here, the congressional challenge was the quality and precision of the optics were totally unproven and well beyond the state of the art for X-ray optics. So Congress created a milestone, I assume with NASA's help, to demonstrate that the largest 2 mirrors could be fabricated with an and then go through an X-ray test. The performance had to be better than half arc second, full width half max, had to be completed before end of August 1991. And at the time, everyone shook hands because everyone's giddy over winning the contract and actually getting funding. It's only 2 years away from getting that contract going, but there was no X-ray test facility. There was no mirror processing equipment. There was no in-process metrology, the part that we had to do here, and the mirror metrology mount for the X-ray test. There was in-process metrology at PerkinElmer, but the actual verification metrology was part of our job here. And budgets were tight for us. So the first thing we got into was what's called a verification engineering test article. I'm not responsible for the acronym, but the Vita 1, the budgets were really tight for us. Much of the funding was going into getting the mirrors processed in Danbury and the test facility at Marshall Space Flight Center. So the original proposal concept was to replicate the mirror assembly design for this test. In other words, we had a pretty good design concept for the full up assembly. And once people started looking at that and the milestone only being 2 years away, says you can't develop a system this big, this sophisticated in 2 years if you don't even have the equipment to put it together yet. So, and also it was too high a risk to the program when the real technology risk was actually the mirrors. The technology risk, even though the metrology was tough, you know, the structures were tough, the handling equipment was tough, but that had been done on a lot of high precision telescopes. But the actual fabricating of the mirrors and proving that the X-ray reflectance was good and you could bring to a focus these high precision optics with a good image, that hadn't been proven. So they narrowed it down to just being the 2 largest mirrors, providing a focus in a first generation focal plane test. And let's keep going. So the Vita 1 concept, we basically developed our first approach to supporting the mirrors. And it looks more like a lab at RIT as to how some of this first generation equipment. It doesn't look very sophisticated at all, right? You say, okay, you got to come up with a way to support this. How are you going to do this? So basically, we had a custom Newport table, vacuum compatible, so it had to be a little custom work on it. We got some INVAR support stands here, welded INVAR, pretty simple to hold these mirror segments. We have a light baffle here to hide a centroiding mirror here, so you could look down through the system and figure out where the center of the system was. And then to do some alignment of some of that hardware, you know, we had a very long screwdriver to reach down the center, not very sophisticated, but it worked, right? And it was actually counterbalanced. You know, you got to worry about some guy holding this, so it's twice as long as it needs to be. So it's counterbalanced and people can move it in there. If you had a little more time, you could have developed some sophisticated equipment and hoists and dollies, but you know, we were doing things on a shoestring budget. And then the big mailbox here, we also had to do thermal control on this, even though it was in a constant 10 degrees C environment. We still had to do good enough thermal control so that the thermals were managed. That was actually my job at the time, one of the first ones. And all the multi-layer insulation was expired equipment from old programs that didn't need it anymore. and declassified programs. And we said, okay, let's use this, a little of that, commercial heaters. So it was a real kludge job. But in the end, the focus was on the mirrors and making the mirrors focus. So the focus was in the right place. We just had to come up with a metrology mount that met that objective. So of course, the guys developing the mirrors in Danbury, they didn't give us much time. They did. So remember, the congressional milestone was August 31. We hadn't even received the mirrors yet till June 15th. So we had to take those mirrors. We had the mirror integration stand. The mirrors are mounted on 12 flexures around the periphery. I believe it's 12, bonded, held near the centroid for balancing. And we had to get that system. You're trying to minimize as the epoxy cures. You're trying to get rid of all that dimpling that's going to happen around the perimeter. You have really poor stiffness right in this direction on this flimsy cylinder. Even though it's 1 inch thick zero door, you say, oh, that's really stiff. But when you're a meter and a quarter wide, it's pretty flimsy from an optical perspective. From a mechanical perspective, we weren't too worried about breaking it unless we dropped something. Doesn't mean we weren't worried. The assembly was completed. The hardware was shipped to Marshall Space Flight Center, which had just finished their quarter-mile long X-ray tube with an X-ray source at one end and a vacuum tube for a quarter-mile long going into a vacuum chamber. And we brought our system in, and we got into testing. We discovered that the image was very astigmatic. Lots of worry, panic, because the Hubble issue had just happened a couple of years before, or a year before. So everyone say, wait a minute, have we blown it here? Well, we discovered that both our math models and the SAO math models both were predicting incorrect performance in this mount configuration for different reasons, but they were both wrong. Usually you think one of them will be right. But we also discovered, fortunately, some of our best innovative engineers stepped in and looked at this. Gary Matthews and Craig Alessano were two of the leads on this, looked at this, wait a minute, what's this image look like? This looks like classical astigmatism. Is there a simple way to fix that? So they came up with spring-loaded pushers on the side of this structure. It was really the gravity sag hadn't been predicted right. They came up with a constant force spring system, had to modify the mounts for the mirrors, but they were able to do it on the top of those towers, come up with a spring system. They used the Nastran finite element model to say, okay, how much force do we need to get this much displacement out of the system? And basically, they made one adjustment, went back into vacuum, and lo and behold, they met the milestone. So excellent performance was maintained. Congress said, great job, go ahead. But Congress is also looking at the budget with NASA saying, we're not really sure we can afford this mission. so it's like, good job, but sorry. So basically NASA got the team together. Our contract team with Northrop Grumman now was TRW then. Marshall Space Flight Center, Kodak, are some of our best engineers, went out to the West Coast, powwowed with the scientists, say, okay, how do we preserve the intent of the X-ray mission without destroying it? How much of it can we get rid of? So the new concept they came up with after a few months, and there were a lot of naysayers, and there were some, the imaging spectrometer went away as part of this, the XFS. The spectrometer went away, right? And one of the instruments, the original telescope had 4 instruments, and the telescope was designed similar to Hubble, so you could point to any one of those 4 instruments by moving the mirror assembly around. And they had to get rid of 2 of the instruments. And basically, they replaced those. I don't know the voting in the science community. Maybe some of you guys do, but they ended up with a simpler mission, and the high resolution camera and the ASIS focal plane were the winners in that. And they changed from 12 mirrors down to 8 mirrors, so 4 sets of 2 instead of 6 sets of 2. Which, from a mechanical point of view, those mirrors in between those mirrors that we took out were really tight. And mechanical integration, it was a lot of risks that those were going to be hard to do. And as it turned out, they had to also change the orbit from a low Earth orbit serviceable. So the Hubble missions, Hubble serviceability was, we were all excited about it as mechanical engineers. Say, hey, that's cool to be able to repair this thing like Hubble had to do. But in the end, the Hubble repair missions cost almost as much as a new major program, like a new major telescope program. So in the end, they went from a low Earth orbit to a highly elliptical orbit, 64-hour period. That got them outside of the radiation belts, got rid of the day-night cycle around the Earth, so got them to 90% efficiency in the orbit, that they could actually over 50 hours of observation time in a 64-hour orbit. So they basically ended up with more observation time to keep the science community happy. But it wasn't serviceable, but it was still a 5-year minimum mission, and much more viewing time without the eclipses, like I said. So in the end, it was a win-win, and probably saved the program, and this is not an official number, a couple $2 billion. That's what we had heard. So the original telescope looked like this top left picture, and the serviceable instruments with handles, you could actually go up and replace these instruments after 5 years, go to a new technology instrument. Would have been really cool, but also would have been very expensive. So to keep the mission alive, we ended up with this simpler telescope concept that you see there. So the design looks like this, and this is what's flying today. The telescope forwarding thermal enclosure basically attenuates outside this telescope. And by the way, I'm telecentric now, telescope-centric. The spacecraft bus is outside this telescope forward enclosure, holding everything. I'm not going to talk about that much. But basically, the spacecraft has different heat sources, hot and cold, are all around it. So this telescope thermal enclosure around it is basically attenuating some of those temperature cycles around the mirror assembly. So that goes down to the optical bench. The high resolution mirror assembly is there with the stray light shade and aspect determination system camera mounted on the side of it. And there's a fiducial periscope. So the focal planes have 4 reference fiducial lights that go up to the centroid of the mirror assembly. They retro reflect down through, and then there's a periscope that brings the image across the center and into that camera on the side. So as you're drifting and looking at your star field, you have your image acquisition stars and your reference lights all the time. So if there's motion, movement, you can find proof that you're looking where you think you're looking and that you're not moving too much. So what was developed in Rochester is all the structures for the HERMA mirror assembly. The stray light shade was developed with us. The forward thermal enclosure was our design. The optical bench assembly was our design. The telescope thermal control electronics, the mechanism control electronics, the controls for these high and low energy transmission gratings. This composite optical bench, which was the largest composite structure to fly in a space shuttle ever flown. So all that, and we mounted the ball science instrument on the back end. So a quick summary here. The configuration, as Chandra is 8 mirrors and 4 pairs, 33 inches long. Diameters vary from 24 to 48 inches. The weight of the mirrors is up to 431 pounds each. We had to control tilt to 1/10 of an arc second, lateral position to 10, focus thousandths of an inch. The strain, we had to manage the strain. This was really tough to a pretty repeatable and understandable 0.05 pounds and a 400-pound optic. That was pretty tricky. Thermal control to 1/10 of a degree gradient stability and a 1/4 degree absolute temperature stability. Contamination control at 1 degree grazing incidence. 1 micron speck creates a 50 micron shadow. So we had to build and design the telescope and build it for a class 100 clean room and keeping everything super clean throughout the whole process. A lot of programs with precision optics, there's just like one instrument that's highly sensitive to contamination. Because this entire mirror assembly was sensitive, we had to design a purge system to keep it positive pressure inside the mirror assembly all the time. We had to design covers that would keep it sealed once the mirrors were all assembled. had to, wherever it went, when it was shipped in a C5 for testing, the purge cart went with it, kept it positive pressure all the time, right up until, and then when it was integrated with the telescope, then integrated with the spacecraft, the hose, and one of the last things that was clipped at the launch site was to get rid of the purge system, external support equipment. Pretty tough design challenges. Any one of those projects like that purge system, it's like a 3-year project for a mechanical engineer, and his team to pull that off. A lot of these projects were not, because they're so unique, they're completely custom to this type of mission. And the mirror assemblies look roughly like this. You can see the retroreflector. It's not exactly what it looked like, but all the testing had to be done at the X-ray center in the horizontal position. You've got a 10-meter focal length. You're trying to put sources at infinity. They couldn't do infinity, so they went a quarter mile away. And so, but we had to test horizontally. And so basically the whole design of the optical system was designed to be, give us the best management of decenter and tilt in that horizontal position. And we couldn't have metrology that you could put in and take away very easily and maintain the seal you needed for contamination and everything. So this was a pretty sophisticated design. The mirrors are supported on composite sleeves here. These are near zero CTE composite sleeves, and then invar flexures that support the mirrors from the outside. When we were doing Vita 1, we're inside a building with 1 degree temperature control. Then we're inside a clean tent with a 1/4 degree temperature control, and we're seeing the mirrors and then we've got 100 foot per minute air controlled to 1/10 of a degree coming through, and we're looking at the mirrors, and the mirrors during that bonding operation were cycling 1/4 of a degree. Turns out the radiative coupling from the mirrors, the IR, to the wall of the tent, to the wall of the building, was actually enough so the mirrors were going out of spec. And we actually had to turn off the airflow system, turn the lights off. When you turn lights off and on, you could see the temperature change on the mirrors. That's how sensitive we were. So it was a pretty tricky, a lot of learning on the fly as we watched the metrology system, the data through the metrology system before we bonded. I was doing some thermal analysis then. I basically came up, I don't remember the exact numbers, but it was something like the operator, they're in clean room suits. You got 100 foot per minute air. The assembler has to go up and shoot the epoxy in these 12 flexures. I can't remember if there are 4 people around or 3 people around to shoot the epoxy really quickly. They could only stay near the mirrors, even though they're in a full bunny suit, and the only part of their skin that's exposed is right here. They could only stay by the mirrors for like 15 minutes before their body heat would warm up the flexures too much and create too much strain at those 0.05 pound mount locations. It was pretty bizarre. A lot of things drove that challenge, but we solved it with practicing the assembly ahead of time. How do we get there? How can we do this quicker? We did offline practice runs. The team came in, they had their epoxy mixed up, ready to go. Said, go, okay, we're good. The alignment guys had just finished and everything had stabilized. So we knew the mirrors were in the right position from the support equipment. Then you bond those 12 flexures around, you let it cure, and then you verify that nothing shifted after the epoxy sets. Pretty sophisticated engineering job, pretty sophisticated metrology development, but it was very successful. The mirror structures are all composite. You can see in this picture on the right, you can kind of see, originally the flexures were a single piece, but eventually we went to a metal flexure bonded into the composite sleeve, and then a metal puck that basically bonded to the mirror. And we could control the bond line thickness better the way we ended up. And then the mirror could get slid in into these mechanical mounts and locked down. We had to customize building 601. If anyone was around in 1992 or so, they'd have seen that cranes up the top of building 601. Our Kodak building, and they had to expand the roof when they realized they couldn't fit the metrology system in the building. So we had to put a cap on the roof so they could do this 10 and 20 meter metrology system. This is in the Class 100 clean room. Basically, they finished the mirrors. The telescope's actually upside down. These are paraboloids. The aft end of the telescope, the cover, is back in the back of the room there, getting ready to come out and lower it down on top of there. And so basically, we were responsible for developing all this alignment system. There were gravity offloaders. These are big steel weights, basically holding the mirrors. So when we brought the P's and the H's together, you want everything to be offloaded to the 0G configuration as best you can. We're putting it together this way, then we're going to test this way. So tremendous amount of math modeling, as you can imagine, using the structural math models to understand the distortion you'd get in different orientations. And how good is the alignment? The layman's explanation is hitting a hole in one from Rochester to Syracuse, and that would be how good you align the mirrors. So our role on Chandra was more than the mirror assembly, but certainly the high resolution mirror assembly, that was the heart of the system. It's like a set and forget optical system with basically your primary and secondary mirror locked in for life. No ability to adjust it at all, any place in the system. But we also had this fiducial transfer system. This is actually a periscope tube that came across the optical system and reflected light down into the camera. Cameras here, we had to develop access panels on the side so we could get in and install. This is the aspect camera installed there. I don't remember the number. It was like 100 miles of wiring inside the telescope for the thermal control and mechanisms. We had the grading mechanisms, so we had to have primary and redundant features to insert the objective transmission gratings into the field of view. Those had to have a redundant method of operating. It was electrically redundant. Mechanically, they had a fail-safe pin puller that you could pull out and get it out of the field of view in case you wouldn't want one locked in the field of view all the time. So the option was, if one of those gratings fails in place today, you do as much observing as you could with it in place. But once you pull the pin puller and pop it out as a fail-safe, it's out of the view forever. But in terms of the redundancy, that mechanism, the only issue we've had all on the mission with the grading mechanisms on orbit, and I was the manager for that team and did a lot of the design work too, is the fail-safe feature itself that we had to put in. We had to put in fail-safe bumpers and features to unlock and get this out of no matter what position that grading might fail, we had to be able to let it get out of the way of field of view. And one of the few issues we've had on orbit was there's a fail-safe spring in that system, and that was interfering on orbit with our primary operation. And the lessons learned is it's almost impossible to test every feature and every mode of operation on one of these spacecraft. So that redundancy added incredible complexity, making those redundant features to our telescope. But in the end, it's still working 24 years, so I shouldn't say much. The electronics, we had to develop our own electronics here in the group that Dave's in. Now we developed our own thermal control electronics for this system. It's actually a very similar capability to what Roman has, but Roman has gone to proportional heater control and more flexibility. But this system, even back in the 90s, has adjustable set points and wide and narrow ranges and pretty sophisticated thermal control. My team was responsible for contamination covers, the thermal control. A lot of hardware was developed here in Rochester. As with all NASA programs, the test program is a huge issue. I won't go into all the detail, but every one of our subsystems, the Vita 1 you heard about, Vita 2 was actually a structural pathfinder for the mirror assembly. So I mentioned that we tested the mirrors work, but then we had this sophisticated structure with these, multi-million-dollar optics in it. And we wanted to do structural testing on that support system without the final system. So the Vita 2 was actually a structural test article that was exactly the same as the flight, had some of the flight structures in it. And then we were able to put that on our shaker. We were able to do acoustic and various load testing on that system. The optical bench assembly, same thing. A lot of calibration tests, a lot of life testing on mechanisms. The optical bench assembly is pretty fascinating structure. This is, about a 10-meter long optical bench, composite optical bench with an effective thermal expansion coefficient of 0.3 inch per inch per degree Fahrenheit. So that's like 0.1, 0.2 inch per inch per degree Celsius expansion, effective expansion over its entire length. So it's pretty cool structure. It was all designed and developed by our composites design team here in Rochester. We fabricate some composite structures in-house, but we have partners we go to build up these panel sections like you see, but then we bond them, put them together, and create the total final assembly. So basically we're buying the lumber. And this composite optical bench here, you can see, so from the very first picture I showed you, you saw the mirror assembly and the optical bench and the science instruments. So the science instruments weigh about 1,000 pounds, but they're almost 10 meters away. The mirror assembly is a couple thousand pounds, and that's a meter in front of you, and the spacecraft is holding you off these mount points. So huge loads at these titanium interfaces to this optical bench. So the launch loads were like 40,000 pounds. On top of that, this is a man-rated mission. The Chandra mission was man-rated with going up in Columbia. So we had to design for landing loads too. So if the shuttle went up and did its abort because it couldn't make it to orbit, we had to design, those loads were designed so this horizontal mounted system could take that big thump. And some of you maybe remember watching the shuttle landings to see how that rolls over and hits pretty hard. So do you have a question?
What is the purpose of the optical bench?
The optical bench is just a high precision metering structure between the mirror assembly and the focal plane. So, and basically it has precision thermal control on it. So it basically keeps the focal plane aligned with the mirror assembly.
And is there a way to correct for that if it goes out?
Just temperature bench, just temperature control on it. So it has to be there. It's just a passive structure. It's very low thermal expansion. And basically up until 10 years, it was in active thermal control. Now the system's warmed up. So it's just drifting in temperature. But because its thermal expansion coefficient is so low, the focal plane to mirror assembly is staying in adequate focus and alignment now. So it's a high precision structure, but it had to carry, remember, it also had to hold almost 10 meters away. You're holding a 2,000 pound structure on this huge cantilevered structure. So really tough mechanical design problem. These titanium fittings were bonded in there. That was a big project in itself. And then we were responsible, as I said, for the control electronics. So on the front of that optical bench, there was all kinds of mounting locations for these electronic boxes that had to be mounted there. Then the X-ray testing. So while the flight hardware team is designing their systems, we have a test team that was helping Marshall Space Flight Center design the ground metrology system to hold the mirror when it got down to Marshall Space Flight Center for testing, and then to test it. I don't know if you can see this, but this is a tall 3-story building, like 40 feet, I think, at least. And that's the quarter-mile X-ray tube there with the X-ray source way up at the top corner there is the X-ray source with multiple vacuum chambers along the way. And then they could open the doors between sections of the vacuum chamber, get the whole system down to 10 to the minus 5 torr, and basically run the X-rays down through the system. And then there are multiple shutters, quadrant shutters, so they could identify. So it was a really cool X-ray, really good classical metrology program where they could look at different parts of the image. They could cut off different mirrors. So basically, you could look at a quadrant of the system. And basically, that was the calibration for the X-ray instruments. And you can see the flying assembly person there. Had to get creative and how you put some of these systems together. And the offloading system, the loads, similar to what we did for Vita 1 during ground testing. There was an offloading system to account for the horizontal test. Then system integration, this is out at Northrop Grumman. So myself and another 50 assemblers and engineers were out west at Northrop Grumman to install. I was responsible for the contamination cover and grading mechanism teams at that point. And this contamination cover had not been removed, at this point since the X-ray testing. And we had to mount that cover. It's all spring-loaded, so the only way to open it, there was no room to put an active mechanism in, so it was all spring-loaded mechanism with a couple of clock springs and a kickoff spring, and that's what we would have to open on orbit. And these little gold-colored items, those are actually vent valves. So when you launch up, you can't remember the HERMA has to be sealed for contamination, but you needed vent valves on the way up to let the air out. But because it's a shuttle mission, these other three smaller valves, or if you came back in to land, you had to let air back in the telescope. So, these large NASA missions, when you look at the sophistication of some of these features to match every requirement, it gets pretty challenging at times, but it does drive cost. We had to actually develop the assembly tower. And we had a company in California build that for us that we designed. You see the Kodak flag there on the right. So the tower and lift fixtures we developed, the optical bench is all put together at this point. The mirror assembly, everything's mated at this point. Then just before that point, we'd done an acoustic test with a full telescope and the Vita 2. So basically we could verify the vibrations from launch, the acoustical energy going into the optical bench and the structures. And this is not a flight hardware picture, but he was practicing on the engineering test article, having fun. And so here we are. We've moved the telescope from our assembly tower to the Northrop Grumman PRW assembly tower, and we're now dropping the telescope down into the spacecraft. Comes right down to get to this point. And we then went into thermal vacuum testing for a couple months, where we verify the system would work under high vacuum and all the thermal control systems and mechanisms and electronics were all working acceptably. And then launch and flight operations. I haven't said much about this, but Rick Zimmerman was a young engineer at the time and working with us. And this is his picture with Eileen Collins, who was Columbia's, the first STS-93 Columbia's first female commander of a shuttle mission, and she's from Elmira. Is that right? Yeah, she's been here to talk before, not at your group at Kodak, and it was pretty big milestone to have a woman commander for that mission. This is what I call giving the C5 a wedgie. This is the space transportation system, and the whole telescope's inside there, get wheeled into a C5. Talk about requirements. So you're not only man-rated for space, but the C5 has its own requirements for rapid descent and ascent. So that purge system on our mirror assembly had to account for the fact that you might get a rapid recompressurization that you had to keep from imploding on any structures on the mirror assembly. So, pretty sophisticated challenges from these missions. And this is clean room operations out at Northrop Grumman. This is where they were testing the solar arrays that they were properly offloaded and they would deploy. This at Kennedy Space Center, I was fortunate, a real privilege. So this is before 9/11. Okay, so I was actually our team of 3 of us from Kodak and 5 from Northrop Grumman. We got to go out to the launch pad. NASA took us out to the launch pad. The shuttle's on the launch pad, leaning against the space shuttle. This is pre 9/11. It was it was so lax, the security was amazing. Basically got to go up the carriage, go up into the servicing module, which surrounds the shuttle bay. Got to go up there, got to go and inspect the post final assembly, all the closeouts of these thermal blankets and the mechanical connections. And then Rick Zimmerman that you saw was responsible for that final disconnect of our purge system. This vent panel here, this is on the anti-sun side, this little black area. That's a stainless steel mesh, so that's where all the air that's inside the optical bench and HERMA comes out as you go up. But it's on the shaded side of the spacecraft, so it never sees any light, and it's baffled. Got a first level baffle, so there's no stray light in the telescope. And then before we got to this point, though, these are actually in reverse order. This is where the IUS, the inertial upper stage provided by the Air Force, provides 40,000 pounds of thrust. I got to go in to witness some of that activity, and they put you in a special clean room. So a normal clean room garment is pretty lightweight. The clean room garments felt like Kevlar. They're probably fiberglass epoxy with a lining. The clean room suits that you went in to see, they had handles on the shoulders. And I asked the guy escorting me what the handles were for, and he says, "Well, we're loading the propellants here, and they're poisonous. So if you ever have a problem and you collapse, we need those so we can drag you out of here." Oh. So that's like, oh, that kind of hits home all of a sudden, right? So anyway, so that one came off without a hitch. So the IUS with its 40,000 pounds of thrust delivers Chandra after a shuttle gets it into low Earth orbit, gets it most of the way to the final orbit. And then the integral propulsion system on the spacecraft takes you the next step to get into the correct orbit. And this is the launch. There was a fuel leak on the way up, and they didn't understand why they didn't have enough thrust out of one engine. So they kept increasing, ramping up the power to basically the flow rate for that engine. After the fact, and they didn't quite get to high enough orbit, but they were able to make up for it. They got up to a safe orbit, but not as high as they wanted. In the end, once they discovered it wasn't an underperforming engine, it was actually a leak. So this is a lot like the Challenger disaster, and that there was actually extra hydrogen going into there, and you guys are cranking it up, and you just, thank God, nothing bad happened. But anyway, they made up for it. They got lucky, and we made it to orbit successfully. And you can see the astronauts headed out for launch. Not much here. There they go. Page. And the last cameo, this was taken by Katie Coleman, who was a mission specialist responsible for deploying the shuttle, deploying us from the shuttle. There's one other interesting story I should say here at for the 2 years before launch, I was in charge of the launch operations team for Kodak. So we would go to these launch simulations in Cambridge, and NASA would design basically failure scenarios. They say, okay, something's going to go wrong either with the launch, with your payload, with the space shuttle, something goes wrong. We want to see how this team we put together to handle support on orbit is going to react to that failure scenario. So they had, I think there were like 4 or 6 of these scenarios. On one of those scenarios, there was Eileen Collins was on, so you're on the headsets, and all these famous folks are listening. You can't believe you're listening to these people talking on the phone, but you're just having fun with it, right? But anyway, the IUS actually had a single point failure as part of its design with a NASA mission. There was a telemetry verification where you could not verify that you hadn't armed, I think you hadn't armed the payload. So you have 40,000 pounds of thrust sitting in the back of the shuttle bay. And they could not verify that the payload was armed or not. And so this was a mission simulation. It's 50 people flown in from all around the country to support this for 2 days. And we're 5 minutes into the simulation. Eileen Collins asks, on the comm, is asking for a telemetry person, is the IUS safe? Is the IUS safe? They double check. We can't verify this. She says, okay, we're ejecting it. We're out of here. And they have a mechanical fail-safe ejection, spring-loaded ejection, dump the payload overboard to fall into the ocean. And they say that's the end of that simulation. And as it turned out, that was actually planned to demonstrate to the Air Force that that was a real failure. The Air Force actually took an activity to correct that single point failure. And that was corrected before the real mission happened. So it was impressive and scary to see how quickly Eileen had to respond. She's got all this data coming in and saying, wait a minute, and your inclination is, oh, maybe we can figure this out, right? But she's thinking about crew safety and this enormous rocket sitting in the belly of her space shuttle. And she says, out of here. We're not going to hurt anyone here. Big responsibility. So anyway, I probably exaggerated that story a little bit, but it's fun. And a couple more photos that were taken. This was just before that previous deployment. And you can see the shuttle, the Chandra being tilted up and then sprung away just a few minutes later. Kodak moments then started once we got on station on orbit. So on day one, we activated the thermal control system. So myself and our team, we were checking everything out, and that came off without a hitch. Basically, we weren't in the worst orbit yet, but we were stabilizing the system. But we had to wait 18 more days before we could open the cover on the back end, because we've got this spring-loaded passive hinge. And everyone else is so giddy about this mission and how well all the checkouts are going, and I'm just scared to death, because of this mechanism that my team has designed that's passive, and there's no way. There is redundancy, but there's no way to power anything up. It's just like it's either going to go or not. But it popped open successfully, and then the next day, the sunshade door where we worked with Northrop Grumman and the forward cover was tied into their mechanism. Then we had to unlock the grating mechanisms and launch locks. So we got those gratings, so they were launched in a locked position. We had to disconnect these locks and move the gratings out of their locked position. That came off without a hitch, and so the rest was great. And Kodak guys, this was the science instrument guys. So no one from Kodak in these pictures. These are the guys. When they opened the cover and then they got the first few images, I mean, they basically were ecstatic. So it was pretty cool. So, and I'm not going to talk a lot about the images, but the first clear view of the Crab Nebula, I guess this is where we go. This part. So that was one of the first pictures, or it's a newer one of the first pictures. Jet from a black hole, interaction from two galaxies. I'm not going to say a lot about these. There's a lot more description of these. If you go to the Chandra website, again, it's chandra.harvard.edu, they'll take you into a lot of good stuff there. With all these images with much more detailed descriptions of the images. M51, SCA 51, perfect spiral galaxy. And Chandra has gone back to original observations and looked at changes. The alignment is so good, and the changes over the mission, they've been able to compare re-observations of the same target. There are changes, even in the time scale of the universe is so mammoth, and it's only 20 years for Chandra, but there's still change detection. Good image science project, right? And some pictures here. And this was, I just cut and paste this one in yesterday because they're now using Webb and Chandra both. So where you see this black hole and a host galaxy here is what they're looking at here, but this James Webb is giving him more resolution and information, so you learn more about the black hole if you can put it in context, and that's what's happening here. Pretty amazing. Images still coming out. I got a couple more slides if you guys want to hear about current status of the mission and from an
We got 5 more minutes.
5 more minutes? Okay. All right. So overall telescope alignment has been excellent, imaging performance excellent. but we still had some challenges on those grading missions. Early in the mission and intermittent grading, OTG stands for Objective Transmission Grading, a shut-off microswitch occurred, and the investigation revealed that a fail-safe feature, as I mentioned before, was being compressed. And basically that pushed the grading mechanism off the microswitch intermittently. Software timeout feature eventually shut down the motor. So is that someone calling?
No.
No, everything okay? Okay. All right. So the grading would open up, hit the microswitch to shut off the motor, and then this little spring would pop it forward a little bit, come off the microswitch, and then the motor starts it up again, starts it up. So fortunately, people were watching it, and they say, wait a minute, we don't want this thing to go out of its, spend its 5,000 cycles of life on going off and on here. So we found that, it turned out that there's a spherical bearing and a journal bearing, and when you test, the bearings are spec'd for ground test and concentricity. But when you're in a 0 to 90 mechanism, you never really go 360. So that average concentricity never really takes out. What happened was the journal bearing or the spherical bearing was rotating a little bit each time in its shell, and that concentricity difference of a few thousandths of an inch actually made the mechanism move enough so that it was now hitting that bumper spring, causing us to come off the microswitch. So you could never, it's almost impossible to test unless you have a true zero-G test. We did do a offloaded 5,000 cycle test like this, but it never truly got you to that almost zero force scenario that you have on orbit, and the mechanisms are moving. The telescope was designed with a 10 degrees C cold bias, so they're so hypersensitive to contamination on the mission. They wanted to make sure that the optical bench was colder than the mirror assembly. So if there's any contamination, moisture and the epoxy as it outgasses would not get into the mirror assembly and contaminate the optics. So you wanted the telescope to always be 10 degrees colder than the mirror assembly. So I use the term telescope, I should say optical bench assembly. So, but as the thermal finishes on the mission have degraded over time, gradually the optical bench is warmed up so that it's now warmer than the mirror. But fortunately, we're not seeing any issue. But it's interesting that we were probably over-spec'd on that requirement, so we've kind of overachieved, and that's maybe one of the many contributors as to why you're still in good health after 25 years. There's a team of people at the Cambridge Operations Center, Mission Operations Center, and they're constantly looking at these issues. And what's happened now is that the optical bench has gotten very warm, and the aspect camera has gotten warm. And if you remember, the aspect camera has a thermoelectric cooler that keeps the camera focal plane cold for best operation, for optimum signal. And basically, but it was designed to cool to the optical bench as opposed to having its own radiator, because the optical bench is always going to be 10 degrees colder than what that camera needed to run at. As the optical bench has warmed up, that camera has lost its cooling heat sink. So the thermoelectric coolers had to became pegged out, so they're not quite as cold as they were designed to be. So that's been a challenge. So if they stay in the sunny side up orientation too long, where the sun's focusing on the area closest to the camera, you get too hot. But then you have to go to tail sun pitch. But if you're in that position too long, there's parts of the cameras that are getting too hot. And then you go to forward sun, that helps this issue, but then the propellant system on the spacecraft side is getting in trouble. So what's happened, the Cambridge operations team has basically, through their math models and getting the significant well-designed telemetry system on the telescope and all the instruments, they've now come up with ways to predict, okay, if you're looking at this star target, you can stay in this orientation for 7,000 seconds. But if you go to this, but then you have to go to tail sun for a while to cool off that area. But while you're in tail sun cooling off that area, you can look at this target for 4,000 seconds or 8,000 seconds. So it's become a really sophisticated mission ConOps team. But as it turns out, most missions have these constraints that happen after a long time. And some really smart people and smart engineers and scientists are saying, hey, we can solve this problem. This This is just a ConOps problem. And your alignment's so good that if you look this way for 5,000 seconds, you can go back and look at it again for 5,000 more seconds. Put those images together. So some pretty cool stuff on orbit. And I'll skip over these slides. We knew the temperature was going to creep up over time. We looked at all the uncertainties and thermal control and said after 5 or 10 years, there's a good chance you're going to be too warm. We predicted we'd go above that 10-degree point. But as it turns out, we designed the thermal control system. Well, if you warm up the mirror to, say, 25C instead of 20C, we'll just turn the heaters up to 25C and restabilize it. But as it turns out, the mirrors are so stable and the thermal expansion of the structures is so good that they'd rather let it warm up a little bit so they don't create a problem. Because when you put heat in the system, it goes someplace, right? So they don't want to create a problem that fixes the mirror assembly that hurts the aspect camera. So they're running this really cool and efficient operations to keep the whole system in balance, and it's working really good. The first, you can see here, this is, say, the optical bench. This is the temperature gradient across the optical bench for the first few years. And then over on the top, over on the right. And basically, after a while, they had to switch to a different IRU configuration. The IRU inertial reference units, their waste heat goes into the telescope, and that caused a gradient in the bench, but they were able to correct for that. That wasn't considered an issue. But over time, you can see how that gradient has drifted. And then the actual temperature of the optical bench, the target was 10C, and after about 5 years, it stayed in spec. And actually, up until 2016, 15 years into the mission, the cold bias is still, the mirror assembly was still staying in tight temperature control. But since that time, the mirror assembly's gotten warmer, but the mirror assembly started creeping up a little bit. This is one of the mirrors. This is the P1, the largest paraboloid mirror, has crept up in temperature. But again, the coefficient of expansion of the composite structures is almost zero. The coefficient of expansion of zero door is almost zero. So the mirror assembly is working incredibly good because of the basically inherent stable design that was built around it. The challenges are more electronics are hotter than they used to be, mechanisms are hotter than they used to be, and the mission operations team is correcting for that. And then telescope power. This whole telescope only requires the amount of power of a hairdryer. Is all it takes to keep the system running. And they've got ample propellant margin and battery margin for well over another decade, is my understanding. And the encircled energy, basically the mirror performance. And I'll bring this down. The thermal affects the mirror performance, but the gradients across the mirror are small, such that this is, so think of this as your point spread functions spreading out a little bit, 0.12 arc seconds of spread here, so less of a focus. But it turns out that the thermal is only like 8% of the total system budget of 90% encircled energy in 1 arc second, or 0.5 full width half max. But the thermal, from an RSS point of view, is really in the noise of the system after 25 years. So they're not doing anything to change the HERMA thermal configuration other than tweaking the telemetry to get a little bit better accuracy on the sensors or better information from sensors. So there we have it. I'm going to switch. So Chandra continues to operate well thanks to robust design, our talented assembly teams, configurability of the observatory, and the Operations Control Center mission planning team's efforts. Expected 5 years, still rolling strong almost 25 years later. And as long as L3 Harris will have me, I'll keep supporting this mission, mostly because I'm one of the few guys left who actually remember what the mechanism is and how the thermal control system works. And, there's a handful of guys who were like right out of college when we did this mission. They're still around. There's probably 20 people still at L3 Harris who worked on the mission, but they weren't working on my team, unfortunately, on some of this hardware. But Anyway, so that's the history, old news, but good news is it's still working. So, thanks. Any questions? Sure.
I have a question today, that as the technology's improved, what kind of optics and computers and cameras itself, how would that have caused improvements in the qualities of the telescope?
So NASA, it's interesting, NASA just had a competition for a follow-on for the next flagship mission, and probably folks heard that the Lynx X-ray telescope was one of them that didn't win. That telescope concept would be a even more collecting area with a whole bunch of small mirror segments, but precision alignment. So the capability of, say, different types of mirrors is better today. The focal planes would be better. You could have more collecting area in a smaller package. So if the Lynx mission had been selected as one of the ones to be funded for the next decade, then I think there'll be tremendous opportunities in the focal plane resolution, just like James Webb, is looking at similar areas as Hubble is looking, but you're getting phenomenal resolution. And the Roman Space Telescope is going to look at Hubble targets with just new technology, better pixel size, better resolution, more photons than Hubble could get. So,
No, but I mean bigger. Like, how would you expect, if like 2 times or 4 times bigger telescope? How much percent would that increase it?
Yeah, I'm probably not the best person to answer. I know the Lynx telescope had several times, I think as much as 10 times more collecting area. So obviously more collecting area, more photon, better resolution capability at the focal plane. But I'm not sure on that question. Should stick to my engineering answers. Yeah, Dave? Sir.
Is there a deorbit area?
There is a deorbit, but there has been one every few years, but now the deorbit is like, I couldn't believe this number. I thought it was like 100 years out. It's a 10,000 by 140,000 kilometer orbit, and it precesses. It just got down to a 3,000 kilometer perigee. It's changed quite a bit over time, but there's actually almost no scenario forecasted. But there is propellant on board. There was a deorbit to plan in place that they have periodically to revisit every few years. Yeah, that'd be quite a meteorite shower. Yeah, yeah.
I just wondered, what's your best guess for how many years are left? And I said yes.
Yeah. Let's see. I think it's there's a lot of luck riding on the mission right now. The inertial reference units, the cameras, all of the electronics. You think of this mission, I told you when we started in the 80s, we bought the electronics that put this system together, in 1990. Same thing with the focal planes. So they've had failure, like, one of the instruments shut down a few months ago, and it was offline for about a month, the HRC, but they got it back online through some creative remanipulation and cross-strapping of the system or something. The inertial reference units, the IRUs, basically, there's multiple gyros in each IRU. There's 2 IRUs, but one of them's gone, and another one has 2 gone, but they can cross strap and they only need 2. But if you were to lose one of those because it got too hot or something, your mission could come to an end quickly. Same issue that Hubble has. If you lose one of those critical pointing features, or if the ASRAS camera zapped or whatever, then you wouldn't know where you're pointing. So there's a lot of, but based on what I'm seeing in the creativity of the ground team, I'll be surprised if we don't at least make it to 2030, unless Congress kills it before that because of other funding issues. There's no one thing, even the telescope thermal control and mechanisms is all on the first string. It's all got redundant strings to it. It's all got redundancy. They haven't had to use redundancy on almost anything on the mission, except those few areas, the IRUs, couple areas. So I think the potential exists for another decade, but I'd say 5 years is a pretty good bet.
How much does it, so once you get to the end of its scheduled length and you're buying extra time, how much does that cost per year to keep it running? If you know. And then also you have accumulation of scientists and engineers that are working on this, but they're also, some of them are probably migrating into other projects. So do you have is there a nucleus that's going to be able to keep up with it over the next 5 to 10 years?
Yeah, again, I'm not involved in the science explicitly. I mean, Northrop Grumman, like Lockheed, has multiple space programs around. Smithsonian Astrophysics Observatory, they're tied into like the XMM Newton mission, different other X-ray science missions and technology. So I think a lot of they've already kind of like Hubble and James Webb. I mean, they probably got enough data to keep every grad student employed for another 20 years, So I think there's, but the LINX mission, the follow-on X-ray mission that we want to do high resolution X-ray, I think Chandra has a half arc second resolution. The XMM is maybe 10, but much more collecting area. More collecting area. So there's a compromise there. I don't know if that's what you're getting at, but I think there's quite a bit of work for these guys for a few years, but then where does X-ray astronomy go? A lot of these guys have the same skill set to maneuver to go over to other programs.
Do you have an idea of how much it costs per year to operate it?
It's in, I think it was in Space News. I'm sure it's tens of millions of dollars a year to keep these science centers running. Gotta be. Pretty sure Space News had numbers because they're actually, as part of the budget freeze, they were looking at how much does it take to keep Hubble running, how much does it take to keep Chandra running, these flagship missions, and they're still getting good science. So, and now that they can overlap with James Webb, I think there's a lot of some renewed excitement too, that's giving more insight. So, yeah.
You know what the period of high and low energy gradings are? I didn't see anything about that.
I should know. I don't remember. I was in charge of the qual program for those for 5,000 cycles each. I think well, one of them was like at 4,000 cycles, the other one's at 1,000. Unfortunately, I treat them both the same because the mechanisms are the same. So unfortunately, if I was on the science side, I'd probably know more about it. But basically, those mechanisms independently, they were designed for thousands of cycles, and they should be good.
No, I meant the pitch of the grading.
Well, actually, the actual grading pitch, the technical term. Oh, nope, don't know the answer. I could find it. I think it'll be on the website. They actually have a really good link to each of the instruments, and the gratings are under those instruments. The pitch of the gratings, of course. Like I said at the beginning of my talk, I'm in the engineering world versus others. So, yeah.
Again, it's more of a science and it's a bit engineering question, but you mentioned Newton. How are they getting so much hardware choice? Is it because their grazing incident angle is much less? Is that it?
I really haven't studied XMM to understand all the differences.
What 10 angstroms?
Yeah, I had those numbers early on.
But it doesn't matter.
Yeah, no, let's see.
I think that's one advantage of Newton, right? It's harder.
Right. Yeah, I mean, they're complementary missions. I understand. There's a lot.
But Chandra's so much sharper.
Right, exactly. So they complement each other, and LINX was to kind of bridge the gap into a new generation to follow on. So this is just few of the key numbers on the technology, but I didn't, which energy and what the effective collecting area is. Or not wanna.
How involved were you in that 2-year challenge that Congress had given you to prove that the mirrors would work?
I was working at home on on some of the long-term study. They kept the base program going. So at the time, I had 3 young kids at home, and I wasn't one of the ones putting my hand up to go out to the West Coast for 2 months. So my boss went out and a few others. So I wasn't super involved, but I got regular updates, and it was really cool. I mean, I've been in similar activities before where you just get a bunch of technical people together. You try to keep the managers away. You say, hey, we want to keep the same, we want to keep as much of the science as we can. How do we brainstorm this and just come up with how do we maintain the integrity of the mission? Not so much of a change that Congress is going to cancel it and say, wait a minute, that's not what you guys said you're going to build, right? You know, so it's like kind of a balancing act of keeping the science community happy. The engineers saying, yeah, this would be easier to build for us, so we'll save you some money. So it was a really good team, and the reason they were out there a couple months is really to build that teamwork and to get everyone on the same page, because they had a hard sell job, because they had to throw a couple instruments out of this payload. So it was a hard sell afterwards. They knew that everyone was going to be happy. Right? Yes.
I'm curious, how much resolution do you think you might have lost by going from 12 mirrors to 8 mirrors?
I don't know the collecting area. One time I knew those numbers. I just don't know all the numbers. But the collecting area, simplistically, would have reduced by a third. But you still lost. But there was enough overlap in the different energies. But they got some of everything, that's my understanding. Yes, back there.
I think the resolution of the instrument is set more by the overall diameter.
Max diameter.
Set by the fairing. So I think what happened when they descoped from 12 to 8 was they got rid of some mirrors that were in the middle rather than getting rid of mirrors that would have made it really large. So from that point of view, it's likely that the spatial resolution didn't change very much.
Right. Yeah, P1 was critical to keep it the same, and there was a lot of argument about which mirrors to keep. And in the end, it was partially P2 was really hard to fit between 1 and 3. They call it paraboloid 1, 2, 3, 4, and so forth. And basically, there was a lot of argument about that. But the scientists came out on top there by pushing for keep that base. Basically, I think all the original chief science goals were met. So if you look at the high level science goals, they met them. The observing time went up. Almost everything was met in the end, except for that loss of that instrument. That's my understanding. It's quite a challenge. So. How are we doing on time?
Thank you very much.
Maybe we should talk about micrometeorites and JADOS decommissioning.
Yes.
That was
Thank
fun.
you.
That was fun. The first time micrometeorite hit a mirror.
Well, thanks everyone for being here tonight, and thanks again to Keith for the
Thanks a lot. I
presentation.
appreciate it. Thanks for the invitation.